Starting. All attendees are in listen-only mode.
Good morning, good afternoon, or happy lunchtime, whatever the case may be, wherever you are. My name is Jim Raffel, and I'm with ColorMetrix Technologies, and we are going to be presenting the Color Control Myths and Mysteries webinar series part 3 today. Whoops, need to click over here. There we go. So today we have 3 presenters, unlike the previous 2 where it was just myself and Shelby. I'm Jim Raffel with ColorMetrix Technologies. We've been developing color verification and process control software for close to 20 years, primarily in the graphic arts and the printing industry.
I'm Shelby Stepusik. I'm the project manager at ColorMetrix. I've been with ColorMetrix for about 3 years, but before that, my background was in newspaper production. I did that for 17 years at different places around the country, so a lot of pre-press.
And our third presenter today is Chris Brown. Chris, do you want to take a moment and introduce yourself?
So my name is Chris Brown. I'm the engineering manager for Mutoh's Advanced Engineering Group here in Phoenix. And I've been with Mutoh for 17, 18 years. And we do a lot of the work on development of peripheral devices for the printer related to colors. So we designed the SpectraView instrument that plugs into the printer and some of the other related technologies with that.
And Chris is also our G7 expert as certified by Ideal Alliance. So as we get towards the end of the presentation, Chris will be explaining how G7 and the G7 method is being worked into Mutoh's ColorVerify solution, which we helped develop. But before we get to the quote-unquote sales pitch, we really want to give you some straight and pure educational values. So I'm going to point out that we are using the GoToWebinar platform. So those of you that have joined us before know that we don't acknowledge, and I think we even have turned off the hand raise option, which you may or may not have used in other GoToWebinars. Instead, we ask that you look for the question box, which is somewhere in your GoToWebinar control panel. You can click on that, drag it out, type your questions in there, and we will read them, either answer them verbally, or if it's kind of a one-on-one thing, we'll type a response to you. And with that,
So we show this slide at the beginning of every webinar in the series. This is our door to consistent color, and our hope is that by the end of part 4, which will be next week, next Friday, same time, same place, that we will help you get closer to opening the door to consistent color. So when we're looking at this, we're pretending that our targets is the 2 top red squares on either side, and when we try to print, we're getting either that middle or bottom, and we're not matching our target colors. So our agenda today.
did we want to ask the poll question before you do that? Oh, no, you're right. It's next.
No, not yet.
I'm sorry.
I'll prompt
I'm
you
ahead
when
of
it's
you.
time for that. Our agenda today, we're going to do a really quick review of part 1 and part 2. And then we're going to talk about the history of CIE Color Space from 1931, explain LAB a little bit more than we did last time, discuss the reasons for multiple delta E formulas, and as we mentioned earlier, we have Chris Brown here with us to discuss the G7 method.
So why don't we ask that poll question now? Oh, there it is. It's in the wrong spot for some reason. Okay. So what we want to know is if you've joined us for either of the previous webinars or possibly both. So we'll give you a few seconds to answer this question. And we're really just asking this to just decide how much we talk about these next 2 slides. No? Shelby says no, so I must have misunderstood earlier.
It's okay. It'll still help.
All right. All right, that looks like most people have answered. So and I'll share the results with you so you all know. Looks like about half of you are here for the first time, so that's great. So we'll definitely take a moment to go over the previous 2 webinars and let you know where you can find the other 2 parts.
But first, we usually do a little visual demonstration,
I
so
know.
That's why Jim got a little out of order here, but that's okay.
I know. We're disorganized this morning, I guess, but that's because I'm not listening to you. All right, so actually we have another poll question. Because the whole point of this webinar series is to explain the importance of color control, one of the things we like to point out is how easily the human eye can be fooled. So as you look at this screen, there are 3 oranges up here, the 3 orange squares, and they're surrounded by different assortments of colors. So our question is going to be, what should have been the first poll question if I'd have done this correctly, is, are these oranges all the same? So if you guys can take a moment and answer that. See, our audience is getting too smart for us, I think.
I actually think of all the illusions we've done over the webinars, this
Yeah,
is the easier
this
one.
This one's pretty easy, I agree.
But
Give you guys a second to weigh in if you haven't. All right, I think we've got all the answers we're going to get. And it looks like most of you weren't fooled, so, which is fine. Some of that is, anyone who attended the previous webinars knows that I've used illusions like this. And it really is, Shelby's right, this is probably the easiest to tell of all of them, but it still points out that when that line isn't there, if you look at, when I look at it, the one in the upper right corner does look darker than the other 2, and that's caused by the surround lighting, or the surround colors, actually, I should say.
So since about half of you have not attended parts 1 and 2, I want to mention that you can see the recordings of both and this one after we're done with it today, or sometime over the weekend we'll get it posted. You can see that at colormetrix.com/Mutoh webinar.
And we do share that link at the end.
We do. So part 1, what we did very simply is we gave you 5 different color myths, or printing and color myths, and we went and debunked them basically. Myth 1 was you can trust your eyes when it comes to color. 2 was your printer will always match your proof. 3, that substrate has no effect on color. 4, that prints will look the same in all lighting conditions. And 5, that reprints will always match the original production run. In part 2, thank you, we talked more about color perception. We're going to talk a little bit about the human eye again today. We discussed RGB versus CMYK color theory. We gave you a brief LAB introduction. We'll talk a little bit more about that today as well. We described what the functionality for spectrophotometers, and we did some delta E explanations with visual samples. And we'll talk a little bit more about delta E today as well.
And the spectrophotometer, just for those of you, because we don't really talk about it in this part, but it's important to the purpose for all these webinars. That's a color measurement instrument, and when Chris Brown mentioned the Mutoh SpectraView instrument, that's an example of a spectrophotometer. So we had some images of that and explained how that type of instrument works. So that's mostly in part 2. So that's a good one to go back if some of this stuff interests you when we get all done. Oh, it's my turn. So our first topic for webinar 3, our first new topic, is the 1931 CIE XYZ Color Space. So what this is a visual representation of it, which I'm going to bring up again after I go through a description of it. But what this is, it's the first mathematically defined color space. And it was created through an experimental method involving humans viewing colors. And it occurred in France, I believe, and as you might imagine, in 1931. And it basically created what we now refer to as the standard observer. And the standard observer is actually a collection of human beings who actually viewed colors, and through questions and answers, they basically were able to begin to mathematically define the very first color space. So this all worked because when you get right down to it, as accurate as a spectrophotometer can be measuring color, it is in fact a mathematical equivalent of what the human eye sees. So I'm going to let Shelby take over on this slide.
This is actually a slide that we used in part 2, but it's a good reminder that while you can say that the best color comparison tool is the human eye, it is affected by light and the angle of light. So when you are looking at this illustration as an example, the green square or green box on the lower left is more green, while the one above it is more blue, based on the angle of the sun and the way that this person is viewing it.
And these are variables that they tried to eliminate during the standard observer testing. So basically that required that they limit, or tried to limit, the viewer's angle of observation to these colors, what they call a 2% angle, or 2% field of view. And the reason is that has to do with the fovea in the human eye, which I'm going to show you in a moment. And the fovea is basically loaded with the cones that are in your eye. And the cones in your eyes are tristimulus. So the whole mathematical formula is designed to mimic or interpret what your tristimulus receivers in your eye are seeing. So here's what your human eye looks like, and you can see that at the very back of the eye, behind your the opening in your eye where light comes in, is the fovea, and it's straight back, and that's the largest concentration of cones in your entire eye. There are cones throughout your entire eye, but most of them are where the fovea is. So that's where you see color, and the rest of your eye has the rods, which are essentially grayscale, and that's where you see your detail. So when you're doing color viewing, you want to basically be looking straight on and having as much of the color as possible hit the fovea.
And so basically what they were trying to do is they were trying to map a range of those physically produced colors. And what they came up with was this 1931 standard observer of CIE XYZ.
And and again, it's the standard observer, which is really the takeaway from this portion. And because of yet all these standard observers, they were able to mathematically mimic the human eye and create the XYZ color space. And that's what you see here. This is how you would plot a color in the original XYZ color space. You've got X along the X-axis, Y along the Y-axis, as a traditional graph would be. And then the Z in this case is all the way around the outside of the colored shape in the middle. That's your Z coordinate. So it's kind of complicated to plot colors, but depending how well you can see these, it shows you where your different colors are. Your red is in the lower right, your green is kind of in the upper left, and it looks like the rainbow just put into a funny shape. So the color space that you're probably more used to working with and you may have heard of is L star, A star, B star, or just lab color. Some people abbreviate it. That's just mathematically derived from the XYZ color space, which we just showed you.
Good. Yep. You can keep it going.
I can keep going?
Mm-hmm.
Okay. So this is what the LAB color space looks like. And it takes the lightness or darkness element of a color and puts it along what we call the L axis. So that runs right through the middle of the color space, with the darkest at the bottom and the lightest at the top. And I always like to tell people, envision this as a sphere or a basketball. So if you wrapped a basketball around this image that we have here, the lightest colors would be at the top and the darkest colors would be at the bottom. But that would be the grayscale. Actually, the most saturated colors would be at the 50. So at the 50, if you went all the way out to the edge of the ball, your reds would be most saturated, your greens would be most saturated, your blues would be most saturated. Because if you think about it, if you went any lower down, it would start to turn into grays and blacks. So at the middle of the ball at 50, an L of 50 is where you generally find your darkest, most saturated colors. And you can see that you've got an A axis that runs from red to green. So plus A is red, minus A is green, and then a B axis that runs from negative B, which is blue, to plus B, which is yellow. And that's basically the L star, A star, B star color space that you've probably heard colors referred to in.
I like this example.
You like this example?
I do.
Do you want to describe it?
No, go ahead.
Okay. So we're mixing this presentation up a little bit, but the rows on the left is obviously yellow. And so if we look then at the L star, A star, B star values of that, we can see that, look at that, sure enough, the L is 50, so we're very close to the center. So it's a very saturated yellow, probably. And then it's got an A of 8 and a B of 54.53. So just think back to that LAB color space and try to think in your head where those colors would be.
And we do have a poll question.
We do.
Before we get to the next slide.
Right, but let's talk about the LAB of the red. So the red, look at the L, it's 29. And now do you remember, is an L of 0 dark or is an L of 100 dark? Think about that for a second and figure out where in the AB axis, the L axis you are. And then an A of 52 and a B of 22. Also, before we do the poll question, this came from, and you can just Google it, X-Rite has a great book that you can now download as a PDF, and it's just called A Guide to Understanding Color Communication. A lot of great images and examples like this that you can refer to. I want to at least give them credit for that. So the poll question here is, do you think that you could plot these two colors just the A and the B. Don't worry so much about the L part. The L is actually fairly easy. But do you think you could plot the A and the B? And there's the reason we're asking this. So go ahead and answer. There's no right answer, no wrong answer. We're just kind of curious how well we're doing explaining LAB. And there's also an alternative color space we're going to talk about that I personally think is easier to plot colors in. All right, so I think most of you are going to answer have. And it looks like about 3/4 of you, 80% of you, feel like you could plot the colors. So that's good. That means we've done a decent job at least explaining LAB. So here's those two colors plotted in the AB coordinates at least. And just so you know, the yellow flower is actually inside the red circle. And those two circles moved a little bit. The A, that's your yellow flower, and the B is the red flower. And I had these circles around them in the alternative colors so that you could see them, obviously, because the yellow wouldn't show up too well against yellow. So if that's about where you thought those colors would be, you got it right. Now, let's talk more about the L component of color. That's the lightness and the darkness. So we mentioned that the original flower we showed you was a 52L. This one on the right is a 64L. And so right away you can see that it's lighter. It's kind of washed out. It may have been printed incorrectly. And remember, it's got a larger L, so it's lighter, because 100L is as light as you can get. So the way that would look, I don't think I actually have a plot of that, but one of them would be right here around 50, and the other one would be way up here around 60. So you can see it's moving away from dark and towards light.
So if you think about the chart we keep showing you, which was on the previous slide, the way that you calculate delta L is the difference between the light and dark. Plus is lighter and minus is darker. And then delta A is the difference on the red and green, with plus being redder and minus being greener. While delta B is on the yellow-blue axis, with plus being yellower and minus being bluer. Now, if you take all of those and do the math, that's your delta E. That's the total color difference.
Right, and that's often the way that a manufacturer might refer to, if they give you a quality specification, a color quality specification, they might give you a set of LAB coordinates, and they might ask you to hit it within a total delta E of 2 or 3. And that's taking all of the different deltas into account. But it gets more complicated. There are what we call multiple delta E formulas and tolerance methods. So I'm going to run through these quickly. And again, the purpose of these webinars is kind of a 10,000-foot view to get you exposed to some of these topics that you may or may not have been exposed to before. And again, I'm referencing the source that I pulled a lot of these images from. And then I also have very detailed written descriptions. That's X-Ray's Guide to Color, Understanding Color Communication. Great document that's out there as a PDF. So the original and the delta E formula that we've been talking about up to this point is commonly referred to as CIELAB delta E. It's a cube, and that's what the image here is showing. The standard's in the very, very center of the cube, and the tolerance box is evenly sized from top to bottom, left to right. And again, it's 3-dimensional. And there's some problems with that, because that's not the way that our human eye differentiates and sees color all the time. There's certain colors that this is great for, and it works just fine. Honestly, some of the numbers I've heard tossed around is that about 75% of the time, this tolerancing method is just fine. And it's still used quite a bit today.
But then I think it was in the mid to late 1980s, CMC, which I think was Color Measurement Committee out of Great Britain. I think the actual name of it was longer, but CMC. They came up with a new way for calculating delta E, and it was where CIELAB was rectangular, they went into elliptical. So we have LCH now. Now L is the same as it was in LAB. It still represents lightness and darkness. So you still have that axis. But C is now chroma or saturation, and it's plotted out from the center outward to the circle or the elliptical. And then H is actually the hue, the color, and it's now plotted in angular. So 360 degrees, starting at red all the way around. So if we're talking 180 degrees, think about that axis again. We're going to be in the green area. And if you're talking 359, you're going to be all the way back around into that red area.
So, and you might remember that I said it was kind of my earlier poll question was a trick question, because honestly, remembering where to plot those colors in LAB is kind of hard. You have to kind of visually picture the graph or look at the graph. LCH is just, to me at least, is a breeze to plot, because I go up or down the L. The C is always to the right. You always start from the center and go right, and then the H is always 180 degrees. So 0 is red, 90 is yellow, 180 is green, 270 is blue. So you can kind of keep those. That's all you have to really remember in your head, is where, that the circle goes red, yellow, green, blue. And I can very quickly look at a set of LCH numbers, and I know where they are visually in the color space. At least it works better for me. And that's just kind of a side benefit. I guess they had to come up with this method in order to properly calculate the CMC and elliptical tolerancing methods. So,
but what's nice about that too is you don't have to think in three-dimensional as much as you do with LAB, I think.
Right. It's still three-dimensional, but you don't have to think in 3 dimensions. You're right. I agree. So I mentioned elliptical. So here, the reference is still in the very center of the ellipse, or think egg, but the human eye sees L, lightness, chroma, and hue all differently, and the human eye also sees those things differently depending what color you're looking at. So these elliptical color spaces, using what they call the CMC formula, they basically get you about 85% representative of what the human eye will see. The CIE 2000 tolerancing method gets you to about 95% representation of what human vision is.
So here's looking at that same kind of chart, but looking at it with ellipses. And the thing is, we as humans just don't see color all the same. So if you look at I know this might be a little hard to see, but if you look at where the green ellipses are on the left-hand side of this circle, and look how big those ellipses are. Now try to see the orange, in between the yellow and red, of course, and the upper right quadrant. Look how small those are. We just have more of a tolerance for green than we do orange, and our tolerances become smaller as lightness increases and decreases.
And also a saturation. If you look at the ellipses in the center, they're very small. And if you look at the ellipses on the outside of any color, they're much bigger. So once a color is fully saturated, we have a harder time differentiating color differences as when the color is very light. And think about light colors, that's your neutral grays, your flesh tones, things like that are critically important, yet we have the least tolerance for them as human beings. So when we talk about the delta E's, there's a bunch of them. This is the 3 that are most commonly used, at least in the industries that I am active in. That's the original CIELAB delta E, about 75% accurate to the human eye. The CMC 2.1, which is about 85 to 90% accurate to the human eye. And then 2000, which is really becoming the most common one and is used by the GRACL, is now, I think it's now technically recommended by the GRACL committee. It's a CIE 2000 formula that's about 90 to 95% accurate to the human eye. And if it's not currently, it's at least up for vote in the international committees that we switch to that one for things like the G7, not necessarily the G7 method, but the standards upon which the G7 method is based. So again, these are all comparative to the human eye, and as cool as all this color math is, if it doesn't relate back to the human eye, it's really not going to do us a whole lot of good. We just have to understand that some human eyes have deficiencies. For example, I'm an older male. I don't see yellow as well as Shelby does. Neither one of us is going to see color as well at 2 in the morning when we're tired and fatigued as we would at 9 or 10 in the morning when our eyes are fresh and we've had sleep.
And because it has 90 to 95% accuracy compared to the human eye, we do suggest if you're starting out that you do CIE 2000. But no matter what delta E formula you pick, you should pick one and just stick with it, because you don't want to be comparing one to another. To a different one. You're not going to get apples to apple comparison. It's possible that your customer may pick it for you. In part 2, we actually talked about how you may have to go through and find out what your customer's delta E tolerance is. But yeah, depending on where you are in the industry, you may find that one is more popular than another, and that should be your standard.
All right, so we are about to turn the presentation over to Chris Brown from Mutoh, but before we do, we want to give him a little bit of heads up. So we're going to ask you a poll question here, and basically we just want to know how familiar you are with the G7 method and the organization behind the G7 method Ideal Alliance. So if you could all take a moment, let us know this. It will help Chris in the level of detail that he gives over the next couple of slides. Also, while you're all taking a second to answer, I'll let you know that Chris will also be part of part 4 of the webinar, which is next Friday, when we will do more detail about the G7 method and creating curves and things like that. We will be doing a demonstration of the new curve making software that is part of the Mutoh ColorVerify solution. Looks like we've got all our answers in, Chris, and I will let you know that you have, I guess you have about a 50-50 sort of, close to. They've never heard of it, or they're very familiar or somewhat familiar. So that should help you tailor your presentation. So let me get to Chris's first slide and turn it over to him. Go ahead, Chris.
All right, thank you, Jim. So far at this point we've been talking, I think Jim and Shelby have been talking about color management at the general level. We wanted to touch a little bit this session to describe what Mutoh is doing in implementing G7 as part of its process control solution, which we'll get into more in-depth next Friday, as Jim mentioned in session 4. But basically what we're doing is we are implementing G7 calibration in lieu of the traditional linearization that I think most people in the industry are familiar with. So typically when you build a profile for your printer, the common way to do it, it varies a little bit rip to rip, is you linearize, you may set some ink limits, you do your linearization, and then you build your ICC profile. So what we're doing is we are removing the linearization step, and we are replacing it with a G7 calibration. And in effect, by doing that, we gain a couple of key advantages. The first one is that with linearization, you are effectively calibrating the printer to itself. So you're calibrating the printer, you're linearizing the printer to a particular arbitrary condition that it is at when you perform that linearization, but you don't necessarily know that when you relinearize that printer at some point in the future that you're going to get the same results. What G7 gives us is a set of aim points that are machine independent, they're industry independent, and these are aim points that are defined in what's called, it's a report called TR015, it's ANSI CGAT's technical report, TR015. And what that report does is it defines what the G7 aim points are, so that anyone with any printer calibrating the G7 will be calibrating to the same set of aim points. This allows us to always get the printer back to a common condition, regardless of the printer, regardless of when we're doing it, the ink or the media we're using, we're always calibrating back to a common reference point. We still do set initial ink limits, and this is really dependent upon the machine and the media and the resolution we're printing at. It's not always necessary. Sometimes it is, and it's really just if we're in a situation where because of the resolution or the media that we're printing with, we're simply putting down too much ink on the chart to make it readable by our instrument, then we set some initial ink limits. And if we do that, those ink limits simply get rolled into the G7 curves. So once set, then those get rolled in, those become part of the G7 calibration. There are no more patches than standard linearization targeted. So if you think about your conventional linearization target and its size and how long it takes you to measure that, the G7 calibration is no more than that. In some cases, it's actually fewer patches that you're measuring. So it takes no more time, so we're not adding any additional steps to do this. We're simply replacing one step with another that takes pretty much exactly the same time, same point in the workflow. And what we get when we do that linearization is that we end up then with a set of curves, one curve each for C, M, Y, and K. So you kind of get the same data points that you would get if you did the linearization, but the curves are going to be very different. And then what we do is we then import those curves into the RIP software in lieu of the linearization curves that you would normally have. And again, by doing that, what we've then done is when we then print a test chart on that to verify that we have the G7 calibration, we're then able to verify that we've hit the same aims, and if I do that on multiple printers, all those printers are going to be hitting the same aim points. So what we're doing with G7, very simply, is that we are calibrating to a neutral grayscale. And that is a neutral grayscale that is defined in TR015. It's adapted to your media and your media white point and the L-star of your process black of DMAX. So you're basically, once I know, or once the software knows the colorimetry of your white point, your LAB of your media, and we know the LAB values of the blackest black, there is then a process where from that we can determine what the optimum grayscale setting should be for all of the points in between for both the process black, the CMY black, and the K channel. And the results of that are then the aim points, and we can go back and test and verify that we've hit those G7 aim points. So if something then changes, if my white point changes, if I put on a different roll of media, if I have to change an ink cartridge and the color of the ink that I put in with the new cartridge is slightly different than the one that was there, I can redo that G7 calibration. It'll take those factors into account, and what I will end up doing then is effectively having that machine back to this known good condition that I'm always going to be building my ICC profiles on. So those aim points give us a calibration, give us a point to calibrate back to should color drift occur during a production run. So if I'm in the middle of printing, I can be checking this periodically between my prints, and if I see something begin to change before it gets to the point where it's going to cause a visually noticeable change in my image, I can recalibrate back to my G7 aim points. It's much, much faster than having to reprofile the printer. That's something I can do in a matter of minutes. I can redo that G7 calibration, get back to those aim points, and know that my profile is still good, and I'm going to be able to continue reproducing color within tolerance for that run. In effect, what we're doing is it's giving us a set of knobs that linearization doesn't do. With G7, now what I have is if something begins to change in the middle of production, I've got a tool, I've got a set of controls that I can redo, I can reiterate those curves and dial my machine back to this condition that it was in when I built the profile. So for this reason, G7 becomes an excellent foundation upon which to build our ICC profiles, because we're using G7 to get the printer into a known good condition, which I can duplicate at any point. I can build my ICC profile on that, and as a result, I'm going to be able to use that profile. It's going to make that profile much more effective over time, and I'm going to be much more confident in the reliability of that profile as I'm doing this production run. Because all of my equipment is calibrated back to these common aim points, it also takes the visual appearance of the images coming off the printer, even before I build the ICC profile. It takes the visual appearance and brings them much closer together. So as a result, when I then go to build my ICC profile, my profile is doing a lot less work to match color. Because with G7, at least my grayscale, which is very important to the overall visual appearance of an image, is going to match very closely, and so therefore the visual appearance of the images that I print on all these different machines will be very similar. And I'm talking not just printers, not just inkjet printers, but if I'm printing on digital presses, if I'm printing on traditional offset presses, all types of hard copy devices, once calibrated as G7, will produce output that is visually very similar.
Chris.
And then when we build the ICC profile on that, it works very well.
Chris, just to tie back to
yes,
I wanted to tie back to the delta E ellipses that we showed, the CMC and the CIE delta E ellipses. Chris pointed out how important it is that the G7 method linearizes your gray points, and think about that. That's the middle of the AB or CH circle, where those tolerance ellipses are so small. That's where the human eye sees color so much more accurately. And that's why the G7 method is so successful, because it takes, as Chris said, the most critical part of your images and essentially almost takes care of them for you. Although, as Chris says in his next point, it's not a panacea. So I'm sorry, I didn't mean to interrupt, but I
No,
just
that's a
realized
very good point, Jim. And one of the things, G7 isn't something new that was developed in the digital age. This is something that goes back to calibration methods that were used with film photography. So this is, this is based on processes that go back decades, 50, 60 years. And one of the things that's very critical to color photography was always the gray balance. And in calibrating the gray balance, because you are right, the human eye, the human brain is very susceptible to or recognizes small changes in grayscale when looking at two images. So if the grayscale matches, if you are calibrating your grayscale to a common set of aim points, and again, you're only dealing with grayscale so that you don't need a lot of patches and you don't need a lot of aim points to know that you're hitting the mark. The overall visual appearance of your images will appear very, very accurately. Now, to that next point, it's not a panacea. It's not going to produce necessarily better or more accurate color images. It's not going to take a bad profile and make it good. What it is going to do, if your profiles are built on the G7 calibration, it's going to ensure that a good profile doesn't turn bad on you. A profile is simply a characterization of a printer at a particular point in time. When you build the ICC profile, it's assumed that the printer is in a known good condition, and if that condition changes, the profile is no good anymore. So you either have to rebuild the profile or you have to get the printer back to the condition that it was in when you built the profile. It takes a lot more time to rebuild the profile, and there's always a chance that even in rebuilding the profile, I won't hit the colors I was hitting before. With the G7 calibration, all I have to do is redo that calibration, and in most cases, I will be able to, unless it's just a radical problem, which is very unlikely. In most cases, types of color drift that we see in the field, G7 is able to take that profile, get the printer back to that known good condition, and keep a good profile still good and still viable. But it's not necessarily going to give you more accurate color, and you still have to be able to build good profiles. This is just going to give you the control to keep that printer in that condition so that profile continues to be viable. The final point that I just want to mention, and this kind of gets into the financial aspect of implementing G7, is that ID Alliance does have what they call a G7 Master certification, and this is for print facilities, so print shops that actually produce output. And what this does for shops that do implement G7, there is a process that they can go through to get a G7 Master certification. And what that certification does, in effect, is it tells print buyers, potential print buyers, that a print provider who is a G7 Master conforms to industry-recognized best practices. And it helps, for the print buyer, ensure consistency when sourcing from multiple suppliers. So, a good example, in a couple of weeks we have SGIA coming up. Mutoh is going to be there. We're going to have a lot of literature, handouts, brochures. We're also going to have a lot of printing done in our booth, various things at different points in the show. So we're going to be using a lot of different print technology to produce all of that. And we're coming from several vendors. Some things we'll print ourselves. Some other things we'll farm out. But it's critical that all of that stuff, when it all comes in to the show, it all looks the same. And so one of the things that we do is we implement G7 process within our printing, and we have our vendors for the other things like the brochures and smaller things, counter displays and packaging, that they also conform. So as a result, everything ends up looking very, very similar. So whether it's a company like Mutoh going to a trade show, or if it's a Fortune 500 like Verizon doing a promotion in a Radio Shack store where they've got packaging and displays and promotions that they all need to look the same. You think about a McDonald's doing a Happy Meal promotion with for a movie, or they've got a lot of different things that have to be printed, and it all has to look the same. This is where the G7 master certification comes in, because all of those vendors conforming to the G7 requirements will be able to reliably produce output that's going to look the same. It's going to be very similar. And so for a print buyer, a lot of print buyers are starting to look for that. It's already very common in industries like offset. It's becoming more common within our industry. And I think going forward, we're going to see more of that, where that G7 master certification becomes important. So implementing G7 process control is a key step towards securing that. If you can do that, you can secure that certification.
Okay, so in order to help us prepare for next week's webinar, we want to ask another question here. Now that you've gotten a little more background from Chris, do you think the G7 method could help color consistency in your shop? Huh. I can't say I'm surprised. We'll give you guys a few more seconds to answer this one. So do you think the G7 method could help color consistency in your shop? All right, I'm about to close the poll question. And I think Chris will like the results. Kind of have an overwhelming yes. That's great, because that's going to be the main core of next week's presentation. So, Chris, thank you for the introduction. And as I said, we'll go more in depth with G7 next week. But today we want to make sure that you got some takeaways. And our intent was that you walk away with an understanding of LAB and LCH. More importantly, the difference between the two, that they basically both plot the exact same point in space. You just get there with a different method. One might be easier to understand than the other, and one also allows the elliptical tolerancing methods. So obviously we hope that you have some better understanding of the delta E tolerancing methods, how to pick a tolerancing method that's right for your shop. And then thanks for Chris giving us a great introduction to the G7 method. It's not a simple thing to understand, even though it actually is fairly simple to implement with the right software. But basically that you've got a method that calibrates your printer to a known set of standard values versus to itself. So that was our intended takeaways today.
And if you missed parts 1 and 2, or simply want to see this one again, we will have parts 1 and 2 are already there. Part 3 will be soon at colormetrix.com/Mutoh webinar. By Monday, you'll also be able to register for part 4, which will be next Friday at the same time, October 18th at 10 a.m. Pacific time. And like Chris and Jim have been telling us, we're going to be talking more about color process control when you need to apply the G7 method. Chris mentioned that we are, all three of us, going to be at SGIA. If you'd like to talk more about this in person, we'll be at the Mutoh booth in number 248. And we do have a poll question, one more, just out of curiosity.
And then we will answer that. We have a question that's been asked as well that I think we'll pose, and I can answer first, and then Chris can elaborate. All right, so our last question is, will you be at SGIA?
If you didn't know, it's in
We're just kind of curious how many people on this webinar will be attending the show. Wow. Okay, well, it started out strong.
SGIA will be in Orlando week after next.
Yep. I certainly wish more of you could make it, but I'm going to stop sharing. It looks like a few of you will be there. I'll share that. So most of you aren't going to be able to make it. So that's the reason for these webinars, is we realize not everyone can make it to a show where we introduce this technology. So, all right. So, Chris, we have a few questions. I'm going to start with I'm going to take them in the order they came in. Jerry asked, what could cause, let me get this back up so I can see it a little better. What would cause a printer's condition to change so much that the ICC profiles become invalid? I know what some of those things are, and I guess I'll give the obvious answers. You could put the easy one is you could put the wrong media in. If you change the white point from what it's supposed to be, that's an easy one to fix. You just put the right media back in. But sometimes media drifts actually enough, depending on where you're getting it, from lot to lot, that white point could invalidate your profile, which ultimately might be able to be fixed with the G7 calibration. Chris, what other kinds of things could invalidate a profile? Do you have any ideas?
Well, yeah. Yeah, we have a few things that we run into both in the field from our customers and then also just within our own facility when we're doing printing. And when you say what invalidates a profile, first, that's a little subjective because it depends on what your expectations are of the profile. So if I'm printing something, for example, I think about our own trade show booth, and if I'm printing something where I've got two panels, it's split across two panels, an image on one side of the booth that you're going to see side by side, we tend to consider that very color critical. So even a very small difference in the overall appearance of those images is going to be very apparent when they're side by side. On the other hand, if I am printing one set for one side and one set for the other, it's far less color critical because it's highly unlikely that you're going to be able to recall the visual appearance of the image on one side of the booth, walk around to it on the other side, see it under completely different conditions, and say, that doesn't look the same. It's going to be way off for you to be able to see that. So part of it depends on what it is that you're printing, and also the expectations of your customer. We certainly do see our customers have buyers, print buyers, that are very critical, and they will go through and they will, take a run of material that's printed, and they will check it with an instrument, and just spot check it and see if it all matches, even if it's not going all in the same place. So the reliability of the profile is very much dependent on what it is that you're printing. Now, what's going to change that, if it's a long run, oftentimes if you're going through multiple rolls of media, one thing that we've had happen ourselves when we're doing things is that we have a roll of material on from a manufacturer, say it's a roll of banner vinyl, and that banner vinyl happens to have a slight blue cast to it, and it may still be within tolerance for the manufacturer, but it's a little blue. We go through that roll, we put on a second roll, it's a different batch, and again, it's still in tolerance for the manufacturer, but this time it's on the opposite side and it's a little yellow. And we start printing and we look down and we say, you know what, those images are going to look the same. We've gone from a blue cast to a yellow cast, and that's throwing off our colors, and it tends to throw off the colors in the highlights, the lighter areas, the midtones, where we're more susceptible to seeing that type of thing. So in those cases, that's where, that profile, which was built on one particular to take, into account the blue cast of the media that we had, can't suddenly take into account the yellow cast. We've got to do something. We've got to fix that. And so what we can do is, in that case, go back and rebalance those, the G7 curves. We can reiterate the curves and oftentimes correct for it, particularly when we're printing photographic images. So again, it's not going to fix things like metamerism. It's not going to fix a spot color mismatch. But the overall appearance of the two images will be brought much closer in line. Something else that we see happen is switching an ink cartridge. Again, in the middle of a run, you run out of magenta ink, you get another ink, it's a different batch, you got it at a different time, you plug it in, as it starts to go through the system and feeds into your printer, you start to see you're getting a bit of a color shift again. So that's another case. And what we're trying to do with this, by implementing a G7 process control, is first, we are periodically running test prints. We're running test charts, which are pretty charts. It's like 100 patches, and we're basically measuring that, and we're checking if we got a pass-fail within a certain tolerance. And depending on how tightly I want to set my my tolerance, I look at that baseline and I say, okay, I'm good or I'm not. And if I get a failure on that baseline, then I go back and I reiterate my curves, my G7 curves, redo my calibration, and reiterate my calibration. And then I rerun that test strip, and if I'm back where I should be, which most cases I am, then I know that I'm back to the condition that I was in when that printer was printing, and everything is going to look consistent. So those are the things that can happen, but again, it's somewhat subjective because it depends on what it is that you're printing, and how color critical it is that you are of the output that you're doing, before you judge whether or not a profile has become unusable.
Okay, so thank you, Chris. Jerry, hopefully that at least began to answer your question. We will be covering all of that in more detail in Part 4. We had a question about the parts being available. Just to reiterate that, Parts 1 and 2 are already available at the URL that's on the current slide, colormetrix.com/Mutoh webinar. I hope to have this part 3, posted by Monday. There is some processing time and things involved, so Monday or Tuesday, though, it will definitely be up, posted. And if you do happen to be one of the people making SGIA, I think Chris is planning to have all the parts burned on CDs that you can pick up there. Let's see.
That's also where you'll be able to sign up for part 4 for next Friday as well.
That you're correct, yeah. Since the boss. Okay, that's just someone pointing out that, I think you're just pointing out that you appreciate our webinars, Regina. All right. Someone wants to talk their bosses into sending them to SGIA. I think everyone should come to SGIA, and because Chris is going to be speaking there. Anyways, we try to keep these things under an hour, and we're at 50 minutes. So it looks like most of the questions have come in. I want to thank all of you for joining us. I want to thank Chris for participating as a guest. I think you added quite a bit to it from the G7 perspective, and we hope to see you all next Friday at noon Central, 10 a.m. Pacific, right?
Correct.
All right, I'm going to end the webinar then.
Thanks again, Chris. Thank you, everyone.
Thank you.